Alrighty, in this video we are going to be talking about increasing, decreasing intervals, and then we'll talk about concavity. As a little review back in Unit 2, we know that a function is increasing graphically whenever the derivative is positive. We also know that a function is decreasing whenever the derivative is negative. And then we know that a function is constant over an interval if the derivative is 0. Or for the most part, because, you might have like that, where you have a horizontal tangent line, which means that the derivative is 0, but we're still technically increasing there. But for the most part, the derivative is going to be 0. We're going to talk about concavity now. If f is concave up, that means that the derivative is increasing, meaning that if the second derivative is greater than 0, f is concave up. If the second derivative is less than 0, aka it's negative, that means that f prime is decreasing. That means that f is going to concave down. We have a point of inflection whenever we change concavity. So going from positive to negative or negative to positive. And then we also have something called the second derivative test. So remember how we had the first derivative test where it tested for extrema. The second derivative test will also test for extrema, except this time we're looking at how it behaves in terms of concavity. So looking at the critical point of C, if f double prime of C is greater than 0, f is concave up. And because we are concaving up, we know that f is going to have a relative minimum at that point. Now, if we're concaving down, you can see that we have a relative maximum. If our second derivative is 0, this test fails, and f might have a relative maximum or neither. You'll just have to see what other methods you could use. The second derivative test doesn't really show up in terms of functions a lot, like number 1 or number 2. It will show up a lot with tables like number 3, or with implicit functions like number 4. So we'll do 3 and 4 whenever we get to it. But for number 1 and number 2, our main goal is to practice increasing, decreasing, concave up, concave down, and then finding our minimum and maximum values. So back in Unit 2, we did this graphically, but now we don't have a graph. We have to do this algebraically. So first things first, take the derivative. When in doubt, take the derivative. So we have first times the derivative of the second plus second times the derivative of the first. Probably factor out a negative e to the negative x. So that you get this lovely thing right here. You know that e to the negative e to the negative x will probably not have a 0. So whenever we set this equal to 0, this means that x is equal to 1. So we have a critical point at x is equal to 1. All right, and then once we plug in, let's say 0 here, this is just going to be 1, so now we have negative 1. 0 minus 1 is going to be negative 1. Negative 1 and a negative is going to be a positive, so this is going to be positive. And then if I plug in a point that's to the right of 1, aka 2, e to the negative 2 is just 1 over e to the e squared, which is positive. We still have a negative here. 2 minus 1 is positive. A negative, a positive will give us a negative. So based off of this information, we know that because we are changing from positive to negative in terms of my derivative at x is equal to 1, we are going to have a local maximum at x is equal to 1. So we don't have a minimum, but we do have a local maximum at 1, and then plug in 1 into the original function to get your output value, or to find the maximum value. In this case, our maximum value would be 1 over e. So by plugging in 1 here, you'll get 1 times e to the negative 1, or 1 over e. Now, because we made the sign chart, lucky for us, we know where we are increasing and we know where we are decreasing. So in this case, we are increasing from negative infinity to positive 1 because my derivative is positive. So negative infinity to positive 1. And then we know that we are decreasing from 1 to infinity. All right. We want to look at concavity now. So in order to look at concavity, we're going to take the second derivative of our lovely function right here. Probably take the second derivative of this right here. So I'm going to do first times the derivative of the second plus second times the derivative of the first. So now we're back to positive e to the negative x. We're still going to factor out to negative e to the x. So that gives us negative e to the negative x. Wait, nope, that's still positive. Wait, no, that's negative. Yeah, so then we get negative x plus 2. All right, so then that means that we are going to set the second derivative equal to 0. So that means that at 2, we have a critical point for my second derivative. Okay, if I plug in something like 0, this is going to be negative. This is going to be positive. So negative and positive is going to be negative. And then if we plug in something like 3, this is going to be negative. This is going to be negative 3 plus 2 is negative 1. So this is going to be negative. So this is going to be positive right here. So we know that we're concaving down from negative infinity to 2. And we're also concaving out from 2 to infinity. I also want to verify that our maximum value 1 comma 1 over e is a maximum value by using the second derivative test. So if I look at x is equal to 1, which falls under this category right here, you'll see that our second derivative is less than 0. Since our second derivative is less than 0, we know that we're concaving down. Since we're concaving down on that interval from negative infinity to 2, in which 1 is included in that interval, we know that we have concave down, aka a local max. So remember that whenever we are justifying our answers, because I didn't do that for the first part, we are going to say that f of x has a local maximum at x is equal to 1 because f prime of x changes signs, and be specific, from positive to negative, and write it out. Don't shorthand this. Change the signs from positive to negative at that point. Same thing with your second derivative test. So if I were to do the same thing where I want to justify that f of x has a local maximum, you're going to tell me that f of x has a local max at x is equal to 1 because your derivative is 0. So f prime of x is equal to 0, aka your critical point, right? And f prime of x is less than, well, not f prime of x, f double prime of x is than 0 at that point. Therefore, we get concave down on that interval, therefore, local maximum. All right. We're going to do the same thing for number 2, where we have x ln of x, and we want to see what happens here. So when in doubt, take the derivative. First times the derivative of the second plus second times the derivative of the first. So we get 1 plus ln of x. If I set that equal to 0, I'm going to get negative 1 is equal to ln of x, which means that x is going to be e to the negative 1 whenever we convert that into an exponential. Now, plot twist, and this is what we need to kind of remember in terms of our domain for this. Remember that the domain of ln of x is going to be from 0 to infinity, so we are going to have to make a stop or a start at 0 and then go all the way to the right. Let's see. Most likely, this is going to be a small number that's going to be less than 1, right? So then this right here is going to be most likely negative. So this is going to be negative. And then if you plug in a number that's greater than e to the negative 1, probably, oh well, let me see, what is e to the negative 1? Oh, yeah, definitely. So then if you plug in 1 here, well, don't plug in 1, plug in like 2 here. Well, yeah, you could plug in 1, because if you plug in 1, that's going to be 0. 0 plus 1 is 1, so this is going to be positive. So because we have negative to positive at e to the negative 1, this is going to tell us that x ln x is going to have a local minimum at e to the negative 1. Now, what's that output value? Well, you're just going to plug in e to the negative 1 and see what you get. Remember that ln and e are constants of each other, so that's going to cancel out, leaving us with a negative 1. So our minimum value is going to be negative e to the negative 1. And we don't have a maximum. Luckily for us, we know that our decreasing interval is going to be from 0 to e to the negative 1. And then our increasing interval is going to be e to the negative 1 to infinity. Remember, to justify your answer, you're just going to say that f has a local minimum at x is equal to e to the negative 1, because f prime of x changes from negative to positive. All right, so we had to talk about concavity. So the second derivative is easy peasy lemon squeezy, because it's just ln of, well, the first derivative is ln of x plus 1. So the second derivative is just 1 over x. 0. Can't really do anything in terms of anything before 0. because that's not going to be part of my original domain. But if I plug in anything to the right, it's going to be positive. So you'll see that here we are always going to be concaving up from 0 to infinity. We're never concaving down. Now, in this case, because we're always concaving up, by the second derivative test, I'm going to write that, f has a local minimum at x is equal to e to the negative 1 because f prime of x is equal to 0 and f double prime of x is greater than 0. Therefore, we're concaving up. So that's why we have a local minimum if I were to use the second derivative test. All right, so for number 3, you are given a twice differentiable function, and you want to find all the critical points, and for each point, to determine if the point is a local min, max, or neither. All right, so remember that I'm not really looking at f of x. F of x is kind of irrelevant in this case. We're trying to look at f prime of x, and that's 0, and this is 0. Now, you can't just say that because we're changing from positive to negative here, that this is a local max, or from negative to positive here, that this is a local min. Because remember that here, this is at x is equal to 0, x is equal to 1, 4, 6, and 9. So we have to use a second derivative test to see what's going on. So we know that x is equal to 1 is a critical point. And we know that because f prime of 1 is equal to 0. And if you look at f double prime of 1, we know that it's greater than 0 because it's 1. Because it's greater than 0, we're concaving up. Since we're concaving up, this is going to be a local minimum. At x is equal to 6, f prime of 6 is equal to 0, and then f double prime of 6 is less than 0. So we're concaving down. Since we're concaving down, we're going to have a local max. So just visually think about what's happening here between the table values and your derivatives. All right, I'm gonna do 4, last one. We consider the function 2y squared minus 6 is equal to y sine of x for y is greater than 0. They gave you the derivative. And for 0 is less than equal to x, which is less than equal to pi, and y is greater than 0. Find the coordinates of the point where the line tangent to the curve is horizontal. So we are going to set the derivative equal to 0, or in this case, set the numerator equal to 0. So y cosine x is equal to 0. Y is greater than 0, so it doesn't really matter there. So cosine x is equal to 0, which means that cosine is, or x is going to be pi over 2. Okay, so if x is pi over 2, I'm going to go ahead and sub in to figure out what my y coordinates are. Sine pi over 2 is 1. So now I have this lovely thing right here, and I need to try and factor this. That gives us -4 and +3. So then, once you do that, and whatever factoring technique you use, you're going to get 2y plus 3, y minus 2 is equal to 0. Y is equal to -3 over 2, and y is equal to 2. Since -3 over 2 is not greater than 0, we don't use that one. We're only using 2. So my coordinate is going to be pi over 2, 2. Okay. Now, for part B, we want to determine if the answer that we found in part A is a relative maximum, a relative minimum, or neither. Meaning that we have to use the second derivative test, aka we need to find out what the second derivative is by taking the derivative, which is not going to be fun because it's implicit and it's quotient. Low, d high, great. Now we have to use product. So we're just using everything here. First times the derivative of the second plus second times the derivative of the first. Okay, so that was my d high, low d high minus high d low all over low square. Looks like a mess, I know, but good thing that our coordinate is pi over 2, because cosine of pi over 2 will give us 0. So anytime I see a cosine, you know that's going to just get yeeted out. That's canceled. That's canceled. Therefore, this is going to get canceled. So now I have 4 times 2 minus sine pi over 2 is 1. Negative 1 times 2. 4 times 2 minus 1. 8, 7. Negative 2. 7 squared. Negative 2 over 7, which is less than 0. Since negative 2 over 7 is less than 0, we know that this right here means that we are concaving down on that interval. Since we're concaving down, this is going to tell me that we have a relative maximum. And how do we know that this is a relative maximum? We need to justify or explain that our derivative at pi over 2 is 0. So dy dx is equal to 0. And our second derivative is less than 0 at the point pi over 2, 2. All right. In the next video that you guys need to watch, you are going to talk about justifying on the AP exam. So more justifying. Lots of fun.